Diffusion models are some of the most powerful generative models we have today. If you ever seen or used modern text to image or video generation systems, chances are diffusion is working underneath. Before diffusion, GANs or generative adversarial networks dominated generative modeling. They were fast and impressive but notoriously unstable to train. Diffusion models change that completely. They are much more stable, scale better, and are especially good at preserving global structure while generating high quality data samples. In this video, we are not going to talk about the full diffusion model. We are going to focus on one specific part, the forward diffusion process. So, and this part alone already explains why diffusion models work so well. At a high level, diffusion models are built on a very simple idea. So we define two processes. A forward process where we gradually add noise to data, and a reverse process, a generative reverse denoising process where a neural network learns to remove that noise. The forward process is fixed. It has no learnable parameters. And the reverse process is learned. So next, it is important to understand that if the forward process slowly destroys structure in a controlled way, then the reverse process can learn to reconstruct that structure step by step, iteratively. So in this video, we will only focus on the forward process because it lays the entire mathematical foundation. So here we start with a clean data sample denoted as x0. This could be an image sample from the training data set. The forward diffusion process defines a Markov chain. So Markov chain is essentially a process where there are well-defined steps, and you take these steps. So there are stepping stones to cross a river, like that. So we move from x0 to x1, x1 to x2, and xt minus 1 to xt, and at the end of the day we will be at x capital T. At each step we add a small amount of Gaussian noise. Formally, we define the forward process using this function q, and the reverse process where we need parameters, we define it as p theta. And so we need to make sure that we have a tractable mathematical equation for this forward process. How are we going to define that? Formally, so we will ignore the reverse process, and formally the forward process is defined as this equation. So this means the distribution of xt is Gaussian. The mean is a scaled version of the previous sample, and the covariance is proportional to the identity matrix, and the identity matrix is multiplied by this constant value. And since images are high dimensional, this Gaussian lives in a very large space. That's why we have a covariance matrix here, and actually this term is a mean vector. That's it. And here you may be able to see that again this is the distribution for xt, and the mean of that distribution is square root of 1 minus beta times the previously sampled value. So, and the variance is essentially this term. But the thing is that what we are doing is, using the previously sampled point, we define the distribution, and using that distribution we sample a new point and use that new sample point for the next step. That's what we are doing here. And so like the previous, though this equation is not really intuitive or like mathematically not easy to handle. And as a result, using the reparameterization trick, we define this equation. This equation is essentially the same. So we take xt minus 1, the previously sampled point, we scale it by 1 minus beta square root, and we add Gaussian noise. So you can think of this in this way. So this is a fixed point, and so we can say this is a deterministic part. This is the stochastic part. This is the term that adds or introduces randomness to the equation. And so that's great. So for those who are familiar with differential equations, this equation is just a discrete stochastic differential equation. And those who are interested in this can go forward and explore more on that area. And so this is going to be one of our key equations when we move forward. And we need to make sure that this Gaussian process really ends up, so this iterative process really ends up in a pure Gaussian noise. And how are we going to do that? So to make sure that happens, we do this simple calculation. This is actually really simple, but though like there is a lot of equations, there are a lot of equations, and it looks a little bit complicated, but I would suggest you to stop for a moment, pause the video for a moment, and try to digest what is happening here, because the idea is extremely simple. So we apply the previous equation to the time step capital T, or the last time step, and so we get this equation. And so here x capital T minus 1 can be replaced by the, like, again applying that previous equation for the term xt minus 1. So we get this, and so we substitute xt minus 1 using this term, and by simplifying it we get this type of an equation. And again we do the same for the term xt minus 2. So at the end of the day we would do this again and again and again until we end up with the term x0, which is the original data sample. And so the original data sample is scaled by this factor, square root of 1 minus beta to the power capital T. And we add these, all these terms are noise, just Gaussian noise, but they have different variances. So we are adding Gaussian noise. So actually these are not variances, this is actually the standard deviation, but as you may know, the variance is the square of the standard deviation. So we have these types of variances for each of these terms. And once we do that, then we can observe something really interesting, because actually I have done a little bit of a mistake here. This beta must be smaller than 1, not smaller than 0. It is between 0 and 1. And if beta is smaller than 1, then this term square root of 1 minus beta to the power capital T is going to converge to 0 as we move, as the T increases, capital T increases. So this means this term is going to cancel out. And from statistics we have this equation where variances can be added where the terms are mutually independent. So since all these terms are Gaussians, they are independent, and as a result we can simply add the variances to get the cumulative variance, which is using series, like our knowledge of series, we can define it in this way. And Actually, since beta is smaller than 1, this converges to 1. So what have we done here? So the mean only depends on this term, because all these terms have the mean of 0. 0 mean unit variance Gaussians. And as a result, so the mean itself is going to be 0 and the total variance is going to be 1. So essentially what we have done here is we have proven that x capital T is a sample from the Gaussian distribution with mean 0 and variance 1 or standard deviation 1. So that's great. And then still there is problem. So before moving into the real issue, here you may be able to see that beta is defined as beta t. Why? Because here, though beta is smaller than 1, it is not a fixed parameter. We are changing it. In other words, we have a forward noising process and noising schedule. So this beta depends on time. But there is a problem with this equation, because suppose you want to calculate the value of xt at the time step 100, t equals 100. In order to do that, we have to apply this equation 100 times. So that is not very productive. So we want to find a way so that using the original data sample, we must be able to directly jump to the given step or the 100th step. So for that we define a new parameter alpha, and this is just to make sure that our calculations are going to be easier. So alpha t is equal to 1 minus beta t, and again we substitute beta t with alpha t, which gives us this equation. Here epsilon t is a sample from the Gaussian distribution, unit Gaussian distribution. So just like what we did previously, we substitute xt minus 1 and do that again and again and again. And here we are doing something really interesting, because these two terms are again Gaussians, and we can add the variances of the Gaussians, which gives us this term. And this is actually the standard deviation, since the standard deviation is equal to the square root of variance, and it is going to be simplified to this. And again we will apply the same idea to xt minus 2, which gives us this equation. So you can see that a little bit of structure is emerging. This term, both of these terms are the same, right? So we do this again and again and again until we get to the original data sample or x0, and we have an equation like this. So we substitute this product of the alpha terms using alpha bar of t, and this gives us the equation which is only dependent on the original data sample, and we can directly, just by using the original data sample, we can directly calculate xt. And this alpha bar of t, these terms can be pre-calculated, and if you want to make sure things are speed enough, you can pre-calculate them and save them somewhere else. So this is going to be our fundamental equation when we move forward and when we discuss the reverse diffusion process. So that's it for this video, and in the next video we will be discussing the reverse diffusion process, the true generative core of denoising diffusion models.